Hey, without further ado, the derivatives of the trigonometric functions. And a reasonable place to start is with the derivative of the sine of x. And we will, of course, use the definition of the derivative. This is the limit as h approaches 0 of the sine of x plus h minus the sine of x all over h. Remember those trig identities that we were looking at recently? Well, the sine of x plus h is the sine of x times the cosine of h plus the cosine of x times the sine of h. So that's all that we've done here is apply that identity. Here I've swapped a couple of the terms and broken the expression into two fractions, factored out a sine of x in the first fraction, and then just rewrote both fractions slightly differently. And now I apply the limit laws. The limit of the sum is the sum of the limits, and the limit of the product is the product of the limits. And as h approaches 0, sine of x stays sine of x. There are no h's in that expression. And by the same idea, as h approaches 0, cosine of x stays cosine of x. Which leaves us with this expression here, the sine of x times the limit as h approaches 0 of the cosine of h minus 1 all of h, plus the cosine of x times the limit as h approaches 0 of the sine of h over h. And all that's left is to compute these two limits, and then we will have the derivative of the sine. Unfortunately, it turns out that I don't have any really satisfying way to show you what these limits are, and so what I'm going to do is show you a graph of one of them so that we can read the limit off the graph, and then although I could do the same thing for the other, it turns out we can compute the other from the first one. Here we have the graph of the sine of x over x, which is not defined when x is equal to 0 because you'd be dividing by 0 and so should technically have an open circle at 0. So imagine that there is one that's too small to see there. But it's certainly clear from the graph that as x approaches 0 from the left and the right, the sine of x over x is approaching 1. And if we change the x's to h's, no difference. The limit as h approaches 0 of sine of h over h equal to 1. That was one of the two limits that we need to compute in order to find the derivative of the sine of x. The other is this one here, the limit as h approaches 0 of the cosine of h minus 1 over h. And if we multiply that by 1 in the form of cosine h plus 1 over cosine h plus 1, we get that it's equal to the limit as h approaches 0 of the cosine squared h minus 1 all over h times cosine of h plus 1. And by the trig identity, sine squared h plus cosine squared h equals 1, we get that cosine squared h minus 1 is actually negative sine squared h. And we can pull the negative sign outside of the limit and break sine squared h into sine of h times the sine of h and write this as two fractions. And then apply the limit law that says that the limit of a product is the product of the limits. And the beautiful thing here is that we know this first limit, and it's easy to take the second limit. The first limit is 1. The limit as h approaches 0 of sine of h over h. And to compute the limit as h approaches 0 of sine of h over cosine h plus 1, we can just plug in h equals 0. Sine of 0 is 0, and in the denominator we get cosine of 0, which is 1, plus 1. So we have 0 over 2, which is 0. And when you multiply that by negative 1, you finally get that this limit is equal to 0. And so now we have the two limits that we need in order to complete our computation of the derivative of the sine of x. In particular, we get that the derivative of the sine of x is the sine of x times 0 plus the cosine of x times 1, or simply the cosine of x. And what we've just done is come up with the very elegant result that the derivative of the sine of x is the cosine of x. All right, let's see if we can compute the derivative of the cosine of x. We again apply the definition of the derivative to get the limit as h approaches 0 of cosine of x plus h minus cosine of x all over h. And we again need a trig identity, the trig identity for the cosine of x plus h. That's just cosine x cosine h minus sine x sine h. Rearranging the term sum and breaking it into two fractions as before, we can again factor a cosine of x out of the numerator in the first term and rewrite the fraction slightly, and then we'll apply the limit laws, and we end up with this expression here. And the beauty of this is we know all of these limits. As h approaches 0, cosine of x and sine of x both stay cosine of x and sine of x, and the other two limits are the exact same ones that we just computed. And we get the cosine of x times 0 minus the sine of x times 1, or just the negative sine of x. And what we have now is the beautiful formula that the derivative of the cosine of x is the negative sine of x. I don't expect you to go through all this work. I do expect you to memorize these derivatives. They'll come up all the time. Derivative of the sine is the cosine. Derivative of the cosine is the negative sine. Well, we've done 2 out of the 6 elementary trig functions. We may as well proceed and do the other 4. I'll start. Let's do the derivative of the tangent of x. I suppose one thing we could do is use the definition of the derivative and work just like we did with the sine and the cosine. It would require knowing some trig identities involving the tangent that we have not looked at, but there's a much easier way. The tangent of x is defined as the sine of x over the cosine of x, and so we can just use the quotient rule to compute the derivative of the tangent of x. And by the quotient rule, that derivative is ho, that's the bottom, the cosine of x, d high, the derivative of the sine of x, which is cosine of x, minus high, that's the sine of x, d ho, the derivative of the bottom, which is the negative sine of x, the derivative of the cosine of x, the negative sine of x, all over ho ho, the bottom squared, that's where that cosine squared x comes from. Simplifying, that gives us cosine squared x plus sine squared x all over cosine squared x. And cosine squared x plus sine squared x is equal to 1. That's our most famous trig identity. And finally, 1 over the cosine squared x is the secant squared x. Okay, to recap, here's what we have so far. The derivative of the sine of x is the cosine of x. The derivative of the cosine of x is the negative sine of x. And the derivative of the tangent of x is the secant squared of x. All right, you finished the list. Find the derivative of the cotangent of x, the secant of x, and the cosecant of x. Do each one by writing it in terms of sines and cosines and using the quotient rule. So take a few minutes, see if you can compute these, pause the video, and when you're ready, start it up again, and we will do it together. Here's the derivative of the cotangent. I'll walk you through it quickly. The cotangent of x is the cosine of x over the sine of x. Applying the quotient rule, ho d high minus high d ho over ho ho gives us this next line there. And then we've got negative sine squared x minus cosine squared x over sine squared x. Well, if you factor a negative 1 out of the numerator, that gives us negative sine squared x plus cosine squared x. And of course, sine squared x plus cosine squared x is 1. So we have negative 1 over the sine squared x, and negative 1 over the sine squared x is the cosecant squared x. And so we have just added to our list of trig identities with the derivative of the cotangent of x being equal to the negative cosecant squared of x. Turning to the derivative of the secant, well, the secant of x is 1 over the cosine of x. Applying the quotient rule yields us this next expression here, where you have to be careful. The derivative of the 1 is a 0, and this simplifies to sine of x over cosine squared x. You will never see it written that way. If you break that fraction up as 1 over the cosine of x times the sine of x over the cosine of x, you find that the derivative of the secant of x is the secant of x times the tangent of x. Adding one more rule to our list of trigonometric derivatives. And the derivative of the cosecant proceeds along very much the same lines as the derivative of the secant. The cosecant is 1 over the sine of x. We apply the quotient rule. You still have to be careful to remember that the derivative of 1 is equal to 0. And we get negative cosine x over sine squared x, which again we can split into the product of two fractions and write as negative cosecant of x times the cotangent of x. And that completes our list of the derivatives of the 6 elementary trig functions. The bad news is you absolutely have to memorize them. You don't want to, yes, you could memorize the sine and the cosine, and then I suppose you could figure out the derivatives of the tangent and the secant, etc., using the quotient rule, but it takes too much time, and this will not be the problem. You know, the problem on a quiz or exam won't be find the derivative of the tangent. That'll be some small piece of a problem, and you want it to be instantaneous. And so the bad news is you need to memorize all 6 of these. The good news is it's not really all that hard. Once you've got that the derivative of the sine of x is the cosine of x, and the derivative of the cosine x is the negative sine of x, there's sort of a pattern here. If you can remember that the derivative of the tangent of x is the secant squared x, then you can probably deduce that the derivative of the cotangent of x is the negative cosecant squared of x. In other words, the derivatives of all the ones that start with the co all are the negative of the corresponding, related function for the ones that don't start with a co. Boy, that was poorly said. In other words, derivative of tangent x is secant squared x, so derivative of cotangent x, negative cosecant squared x. Derivative of secant x times the tangent of x, so the derivative of the cosecant of x is the negative cosecant of x cotangent of x. And if that didn't make any sense, then I'm sorry, you just have to memorize them. So memorize these 6 elementary trig functions, or rather the derivatives of these 6 elementary trig functions. You need to know them. And knowing the derivatives of these elementary trig functions opens up a whole new world of problems that we can solve. For example, take a look at this function, f of x equals the cosecant of x plus e to the x times the tangent of x. And suppose we wanted to find its derivative. Well, the derivative of a sum is the sum of the derivatives, and the first part is not hard. The derivative of the cosecant of x is just the negative cosecant of x times the cotangent of x. And then we have to add the derivative of e to the x times the tangent of x. Well, how do you find that derivative? It's a product, so you have no choice. You have to use the product rule. And by the product rule, we get that it's the derivative of the first times the second, and the first function is e to the x, and the derivative of e to the x is just e to the x, so that's e to the x times the tangent of x, plus the first times the derivative of the second. And the first function is e to the x once again, and the derivative of the tangent of x is the secant squared x. So we get this answer here. Okay, you try this one. See if you can find the equation of the line tangent to y equals 2x times the sine of x at the point where x equals pi over 2. So pause the video, take a few moments, see if you can figure out the equation of the tangent line. When you're ready, start it back up again. The derivative y prime tells us the slope of a tangent line at any point x, and to compute the derivative, we need the product rule because it's a product. And the product rule is the derivative of the first times the second plus the first times the derivative of the second. The derivative of the first is the derivative of 2x, which is just 2, times the second, which is sine of x. And then we have the first function, which is 2x, times the derivative of the sine of x, which is the cosine of x. This gives us the derivative anywhere. We're interested in the derivative at x equals pi over 2, because that gives us the slope of the tangent line at x equals pi over 2. And so we evaluate the derivative at x equals pi over 2. It requires computing the sine of pi over 2 and the cosine of pi over 2, which shouldn't be hard. Sine of pi over 2 is 1, the cosine of pi over 2 is 0. And so in the end, we get that the derivative at pi over 2 is equal to 2. That tells us that the tangent line has the form y equals 2x plus b for some value of b. We have to plug in x and y to find b. We know what x is, it's pi over 2. To find y, we plug x into the expression y equals 2x sine of x. That gives that y is equal to 2 times pi over 2 times the sine of pi over 2. And since the sine of pi over 2 is 1, we get that y is equal to pi. Plugging those values of x and y into the equation y equals 2x plus b gives us that pi is equal to pi plus b, so b is equal to 0. And so we have our answer. The equation of the tangent line to y equals 2x sine x at x equals pi over 2 is simply y equals 2x. Okay, those were the derivatives of all 6 of the elementary trigonometric functions. There is, of course, a homework on it. Have fun with it. See you soon.